Dawson City, Yukon Territory, February 12th, 1905, temperature minus 43 degrees Celsius. The water stops flowing at 4:17 in the morning. Not a trickle, not a drip. Complete silence where the sound of rushing water had been constant for 6 months. In the pump house on the Klondike River, Chief Engineer Thomas McConnell stands in front of a wall of frozen pipes, his breath forming ice crystals in the lamplight. Behind him, 300 miners are sleeping in bunkhouses that depend on this water. So do the stamp mills. So does the entire hydraulic mining operation that employs them. He has 8 hours to fix this before the mines shut down. The problem isn't new. Water freezes at 0 degrees Celsius. Everyone knows this. What's less obvious is what happens to water systems when temperatures drop to minus 40 and stay there for weeks. In Dawson City in 1905, they're learning the hard way. The Yukon gold rush may have peaked in 1898, but by 1905, the real money comes from industrial operations. Hydraulic mining, steam-powered equipment, processing mills that run 24 hours a day through winter darkness. All of it needs water, not in summer when the Klondike runs free and clear, in February, in minus 40, when everything should be frozen solid. Should be, but isn't, because 6 months earlier a mining engineer named Joseph Whiteside Boyle solved a problem that conventional wisdom said was impossible. He kept water flowing through winter, not with insulation alone, not with constant circulation, with a system so elegant that engineers from as far as Alaska and Siberia traveled to Dawson to see it work. The conventional approach was simple. Don't try. Shut down in October. Wait for spring. Most operations accepted this. Winter meant frozen ground, frozen water, frozen everything. Mining stopped. Mills went silent. Workers took leave or burned through their savings waiting for thaw. But Boyle saw something others didn't. The problem wasn't that water freezes at minus 40. The problem was that people treated water as a substance that moves through pipes. Boyle treated it as a heat transfer system. Water at 0 degrees contains heat. Not much, but some. Water at 4 degrees, its point of maximum density, contains significantly more. The question wasn't how to prevent freezing. The question was how to add heat continuously, invisibly, in a way that didn't require massive fuel consumption or constant human intervention. His answer came from mining itself. Deep underground. The earth stays warm, not hot, warm. At 30 meters depth, the ground temperature in the Yukon hovers around 0 degrees year-round, regardless of surface conditions. At 60 meters, it's warmer. At 90 meters, the depth of the main mine shafts near Dawson, it's between 2 and 4 degrees Celsius. Constant, reliable, free. Boyle's system works backward from what everyone expected. Instead of heating water at the surface and trying to keep it warm, he pulls water from deep underground where it's already above freezing, routes it through the operations, and returns it below ground before it can freeze solid. The entire loop stays underground except for the sections actively in use. The innovation isn't the depth. Miners were already going that deep. The innovation is treating the mine itself as a thermal battery. It's if you want to see how a system designed for extracting gold ended up solving one of the Arctic's fundamental engineering challenges, please hit that like button. It helps us share more forgotten stories. Subscribe if you haven't already. Back to Boyle's system. The technical details are more complex than they appear. Pulling water from 90 meters is easy. Keeping it from freezing in the 15 seconds between leaving the underground reservoir and entering the heated pump house is the challenge. Boyle's solution uses gravity, speed, and a design feature borrowed from steam engines. The water never stops moving. The intake pipe runs at a steep angle. Water enters at 4 degrees, flows upward at roughly 6 meters per second, and arrives at the surface still above freezing. From the main reservoir, it splits into 3 parallel systems. One feeds the hydraulic monitors, giant nozzles that blast frozen ground with high-pressure water. One supplies the stamp mills that crush ore. One provides water for the steam boilers that power everything else. Each system returns its water through dedicated pipes that drop back underground at the same steep angle. The water doesn't freeze because it doesn't slow down long enough. By the time it reaches 30 meters depth, it's back in ground that won't let it freeze. The loop is continuous, but there's a second layer to the system. The pipes that run above ground, the ones connecting buildings, the ones feeding equipment, sit inside larger pipes filled with constantly circulating water from the same underground source. Pipe within a pipe. The outer layer never freezes because it's continuously refreshed. The inner layer never freezes because it's surrounded by moving water that's above zero. This is where the engineering becomes elegant. The system is passive. Once it's running, it maintains itself. No boilers needed for the pipes, no crews shoveling coal at 3 in the morning. The mine's own depth provides the heat. Gravity provides the pressure. The only energy input is the pump that maintains circulation, and that runs on steam generated from burning sawmill waste that would otherwise be discarded. On February 12th, when McConnell finds the frozen section, the failure isn't in Boyle's design. It's in the expansion he authorized. 3 weeks earlier, they added a new stamp mill. The engineer who ran the pipes used single-wall construction to save money. Those pipes froze. Now they're blocking flow to everything downstream. McConnell's solution takes 6 hours. He doesn't try to thaw the frozen section. Instead, he cuts it out entirely, reroutes through a spare double wall line that was installed but never connected, and restarts the flow. By noon, water is running again. The mines never shut down. Most of the workers never knew there was a problem. The incident proves something crucial. The system works, not just in ideal conditions. In the worst conditions the Yukon can produce, -43 with no wind, which means the cold penetrates everything. The double-wall pipes kept flowing. The underground loop maintained temperature. The only failure came from someone trying to save money by ignoring the design. Word spreads quickly in mining communities. By spring 1905, engineers from the Alaska territories are visiting Dawson. They see the system. They take notes. By winter 1906, similar systems are operating in Nome, in Fairbanks, and 3 Russian operations in Siberia. The core principle, using Earth as a thermal battery, becomes standard practice for cold region mining, but the applications extend beyond mining. In 1907, the Royal Canadian Mounted Police built a post at Herschel Island using Boyle's pipe-within-pipe system for their water supply. It runs continuously for 11 months before ice buildup forces a shutdown for maintenance. In 1909, the Hudson's Bay Company installs a modified version at their Fort McPherson trading post. It works through 3 consecutive winters without failure. The system's influence reaches into unexpected areas. Yet when the Canadian government begins planning the Alaska Highway in the 1940s, engineers studying cold region construction reference Boyle's work. The principles of passive heating and continuous circulation inform the design of fuel lines, water systems, and heating infrastructure for the permanent camps along the route. Modern permafrost engineering owes more to Boyle than most engineers realize. The concept of using ground temperature for thermal regulation, now standard in Arctic construction, traces directly back to his double pipe system in Dawson City. So does the principle of continuous circulation as a freeze prevention method. Boyle himself never promoted the innovation. For him, it was simply solving a practical problem. Keep the mines running, keep the water flowing. Everything else was someone else's concern. And he spent his later years in the Yukon managing larger operations, then moved into military service during World War I, where he commanded a machine gun unit with the same practical efficiency he brought to engineering problems. He died in 1923, largely forgotten. His water system outlasted him by decades. The last section of the original installation, a segment of double-wall pipe from the main pump house, was removed in 1963 when the mining operation finally shut down for good. It had been in continuous operation with repairs and maintenance for 58 years. Engineers examining the pipe found the design essentially unchanged from Boyle's original specifications. The outer pipe showed wear. The inner pipe was in remarkable condition, protected by the water flow that had surrounded it for nearly 6 decades. Today, Yeah, the principle seems obvious. Use geothermal stability, keep water moving, insulate through circulation rather than static barriers. In 1905, it was revolutionary enough that experienced engineers traveled thousands of miles to see it work. The difference between innovation and common sense is often just time and proof. In Dawson City, where February temperatures still drop to -40, modern water systems use electric heating and sophisticated insulation. They work well. They also consume enormous amounts of energy compared to Boyle's system, which ran on waste wood and gravity. Sometimes the old solutions were better. Sometimes we forget them anyway. The pump house still stands, converted to a museum. Visitors can see the pipe layout, the original blueprints, and a section of the double wall construction that defined cold region engineering for half a century. Most people walk past it quickly, more interested in gold rush stories and frontier drama. They're missing the real story. Not gold, not adventure. Engineering, the quiet, persistent kind that solves impossible problems with elegant simplicity. The kind that keeps water flowing at -40 degrees in the dark heart of winter. That's what matters. That's what lasts.